So we are again studying the same thing. First we studied the characteristic equations, and then we went for the functions of random variables. So in the characteristic equations, we'll try to solve numericals, and then we'll try to solve some of the numericals corresponding to the what you call the functions of random variables. Okay, wherever I am getting stuck up, that also I will tell you. Sometimes integration is a complication job, which you might be knowing better than me sometimes. So we'll discuss that also. So first, we'll take up 53, verify that the characteristic equation, what you call phi x j omega given for the exponential random variable in the appendix A is correct, is what we need to see. So in the appendix A, for the what you call random variable corresponding to the exponential case, right? Exponential case is all right. That is what is to be proved. So this is the Erlang, and this is exponential, and this is the phi. We should get this, right? We should get this given this fxx. Given this, we should get this. Okay. So we'll get what you call, we need to get this using the other one. So going back, let us try to solve that. So phi of x j omega is equal to e to the power j omega x is equal to integral minus infinity to infinity fxx e to the power of j omega x. This is the characteristic equation, and for the random variable, for the exponential random variable, we have fxx is equal to. I'm trying to pause this for the. So now you have the exponential random variable over here for the for the exponential random variable, we have the PDF, which is something like this: fxx is equal to lambda e to the power of minus x greater than 0. From appendix A, I have picked up this. Okay, using this, we can write the what you call characteristic function, which is something like this, where lambda e to the power of minus lambda x is what we need to write for fxx, and that is for x greater than 0. Therefore, limits will be 0 to infinity now. So now this will become, I need to join these e's, and e to the power j omega minus lambda into x dx. So we need to differentiate, integrate with respect to x. So this will give us e to the power of, lambda, I'm just taking out constant. So the same thing, lambda I should have written here, which I might not have written at this point. Okay, let us leave that, but still it is needed. So e to the power, e to the power of j omega minus lambda x divided by j omega minus lambda 0 to infinity. So lambda is missing. Okay, you need to write that. So that is equal to minus, you can rearrange this also, this thing as minus of lambda plus lambda minus j omega by lambda minus j omega. Another lambda is needed here because of this over here, 0 to infinity. So if you substitute over here the value of infinity, you will get it as 0. If you substitute here the value of 0 here, lower limit, then you will get this value as 1. So only the lower limit 1 will just turn out to be minus of minus lambda. Lambda is supposed to be here. So divided by lambda minus j omega, and this is the value. And that is the one which we have in the appendix, right? So given this, we have to find this. Okay, that's what is the solution. Now let us go for the next question there. 56 is what I've taken here. 54 and 55 are similar things for other, random variables in the what you call in the appendix A. That is, you have Laplace and gamma. So I'm not taking that directly. I'm going to 56, which is given the characteristic equation phi x j omega for the Cauchy's random variable found in appendix A, find the Cauchy's PDF is what we need to do, reverse. Okay, so to do that, if you see over here, right, The Cauchy's random variable is having a characteristic function which is equal to e to the power of minus a omega. This is the characteristic function, and fxx will be equal to the 1 by 2 pi integral of minus infinity to infinity phi x j omega e to the power of minus j omega x d omega. And for this we need to replace it by this, that is e to the power of minus a mod omega e to the power of minus j omega x d omega. And that will turn out to be, we need to write when it is taking the what you call the omega is taking the positive negative values, then omega is taking the negative values, then we'll have to write a value plus a omega over here, plus a omega, because there we have minus a omega, right? Minus infinity to 0. And when we have 0 to infinity positive values of omega, then we'll write minus a omega, which is same as the minus a over here. So this will become positive. Okay, omega should be what you call negative when we take minus infinity to 0. Omega should be positive when we take 0 to infinity. That is what we have written over here. Okay, so once we write this, then you can what you call take omega common over here, then this will become a minus jx. Take minus omega common here, then you'll get a plus jx. So now again, you need to integrate this e to the power of omega a minus jx by a minus jx plus again with limits minus infinity to 0, and again the integral for this function is what we might have written here. So 1 by 2 pi 1 minus a minus jx plus 1 by a plus jx is what we have written over here, and that will be equal to 1 by 2 pi a plus jx plus a minus jx by a square plus x square, a plus jx plus a minus jx by a square plus x square, and that will give us 2a it will become, so therefore it will be a divided by pi a square plus x square, and this is the value which we have for the what you call case of the answer for the Cauchy's random variable. Okay, so if you go back over here in the appendix A for the Cauchy's random variable, we'll have that, right? So Cauchy's random variable given the phi x j omega is equal to e to the power of minus exponential of minus a mod omega, then we need to find out the PDF to be this, and that is what we have found. Okay. Next, we will go for the next problem. Okay, 62. The problem number 62, which I want to go over here. And if you see over here, the chapter 2, okay, so 53 to 55 same, 56 to 58 same, even okay, 57 to 59 same, okay. Only this is a little different given the characteristic function 5j omega for the Cauchy random variable found in appendix A. Find the Cauchy's PDF. Okay, so this is what we have found. Now these are a little, what you call a little complicated, and this I have taken in the okay, yes. So I'm getting this problem over here. That turns out to be, for that it will become b squared by omega squared plus b squared e to the power of minus j omega x. Okay, if I try to solve that problem, I'll get b squared by omega squared plus b squared e to the power of minus j omega x. I think this should be for either 58 or 59. What's that? Okay. Okay, let us go back to the Cauchy's PDF. Where is that? Cauchy's PDF is this. Where is this? Gaussian. gamma Gaussian. Okay. One of them, I think, if I'm right, okay, one of them, which is there over here, has to be what you call considered there. Okay. So I'm getting that problem. If you can solve that, that will be quite nice. Okay. Just see this 1 by 2 pi b squared by omega squared plus b squared e to the power of minus j omega is d omega. Answer should be b by 2 exponential minus bx. This should be what? Okay. So this is one of those 58, 59 or 57, which one of those were that. So I'm not going to solve that. This you try to solve, and if you get it, please take a photo of that and send it to me. Okay. So we'll go for the next problem, that is 62, if I am right. Yes, 62. So in the 62, let us see the question. So if you see 61, 62, and 63 all are same, I have taken 62. It is given that the random variable x is Gaussian with a mean 0 and variance 1. The random variable y is obtained from the relation y equal to 5x minus 6. Find the PDF of y. Find the PDF of y. So for this, we need to take here y is equal to, 5x minus 6, sigma x is equal to 1, mu x equal to 0. So y plus 6 is equal to, 6 you can take on this side. So y plus 6 is equal to 5x, x equal to y plus 6 by 5. This is what we have. Fyy is equal to fxx. So, and also the PDF Fyy is equal to fx of the small x is nothing but the y plus 6 by 5, and therefore we have written that, and then internal derivative of this, that will give us 1 by 5. In case a is considered equal to positive, here we have written a is positive over here. Okay. So because it is the Gaussian random variable, we need to write that 1 by root of 2 pi 5 e to the power of minus x minus mu x whole squared by 2 sigma x square is what we have written over here. So x is nothing but y plus 6 by 5, and this 5 is coming over here, and that's why you'll get this equation over here, right? This is 2 into 1, so y plus 6 whole squared, 5 squared, 5 squared will be 25, 25 into 2 will be 50. So we have here the answer as 1 by 5 root of 2 pi e to the power of minus y plus 6 whole squared by 50. So thus we can try to find out the what you call PDF of the variable y. Okay? That is what is expected of us. Okay, we need to find the PDF of the variable y. Now let us go for the next example. 65. Okay, 60. I think 63, 64 are just similar. Therefore, I might not have solved that. 61 is here. 61 is similar. 63 is also similar. I have gone for 65 because 64 and 66 are similar. So I have not taken that. I have gone for the 65. 65 is x is a Gaussian random variable with a mean of 73.16 and standard deviation of 20.35. Probability of x occurs between 50 and 60. So x is within the range 50 and 80. So 50 less than x less than 80 is what is the probability which we need to find. Probability of 50 less than x less than 80 is what we need to find out, given that the mean is this and the deviation is this. So corresponding to that, we will get the solution like this. So mu x is given, sigma x is given, Gaussian random variable is what is expected. P of 50 less than x less than 80 is what we need to find out. And this is nothing but fx of 80 minus fx of 50, capital CDF, okay? And that is equal to phi of 80 minus, this 80 minus the mean 73.16, because we are talking about Gaussian, divided by 20.35, and phi of 50 minus 73.16 divided by 20 minus 0.35. So this turned out to be 0.336118, and this turns out to be phi of minus 1.1380835, whatever it is. You can restrict it to 3 digits or so, and then you can go to the table for the Gaussian distribution, and then what you call read the value from there. Do I have a Gaussian distribution here somewhere? No, this is not Gaussian. So we need to find phi of 0.336118. Okay, to find this value, you can go to the table over there and see what it is. 0.33. So this is 0.3. 0.33 is here, right? Then you have the, so it should be 33. After that, it should be in between these two. Okay, 0.6293 and 0.6331, because the value is somewhere between 0.3 and 0.33 and 0.34. Okay, so naturally it should be definitely more than this value of 0.6293. So you can just try to find out from there the value, whatever we have. So corresponding to that, 33618 is what we have there. And for that, I think I've done some calculations over here. 0.33612 minus 0.33 divided by 0.34 minus 0.3 multiplied by the two values. 0.34, how much is the value? 0.3, what is the value from the table? Both I have written, and plus 0.6293, and hence it's turning out to be 0.6331. 0.6331. Okay, now this will just correspond to the value, which is 0.0038, this total thing, and hence that has to be added to it, and hence we'll get this. Similarly, 1.138035 is what we need to find out. So for values which are given in the table, which is either 1.13 or 1.14. So rest of the thing is that difference 80835 is what we need to check. And if you go back to the table over here, right? So 1.13. So 1.13 is somewhere here. Do we want 1.13? Okay, 1.13 and 1.14. So somewhere between those two values, 1.13 is this, 0.8708, and the next value is 0.8729. Okay, these two values are to be considered, and hence if we go back there, we'll get the value. That's why both those two values are subtracted, and they correspond to 1.14 and 1.13, and hence we have that. The minimum value, which is 0.8708, is written here, and this is the actual value over here minus the lower value 1.13, because we are considering here the lower value. Therefore, we write here minus this. So at the end, you'll get 0.8725, because this total thing will just correspond to 0.0017, and you'll get this. And if you want, because we want a negative value, it will be 1 minus, that is phi of minus z is equal to 1 minus phi of z, and that's why you subtract that, you'll get 1.75, and the range of values to this is 0.6331 minus 0.1275, and that will turn out to be 0.5056. Okay, This is how we can try to find the what we call solution for that. Now let us go to 67. 67 is somewhere here. Dimension and its tolerance are specified to this and this, this is standard thing. This is already a solved example. Same thing we have tried to do. Again, the Gaussian random variable with a mean of this and standard deviation of this. This is the range of values, that is 0.748 to 0.752. Estimate the percent of realization of y that will remain within the tolerance range, which is 0.748 to 0.752. So that's really speaking almost like a solved example, but still I've done this here. Okay, 0.752 and this is 0.748 and this we need to be written it. This is a standard. This is a Gaussian process. This is a normalized or standard Gaussian process by removing the mean and dividing by the what we call deviation. Sorry, rather than the yes, deviation sigma x, and here we will get again the same thing over there, and that is you need to solve that all that because it is a solved example, almost like we have not done that. Okay, so again, if you see the 70 question number 70 there, okay, which is the question number 70 there, which is this. Okay, I didn't know how to represent that. Okay, so you need to what you call show that the characteristic function for Gaussian random variable x with a mean of this and this is equal to this. We have to show this, which is there in the appendix also. Okay, which is there in the appendix also. So corresponding to that, we need to write fxx e to the power of what you call omega x, and we write this, and you need to write it in the proper format. As not getting how to write it in the proper format, please check that up, and it should be such a way that we can write it in the value of phi of that quantity, which is the result which is shown in the question. That is this. We should be able to write in this. I have not solved this. Rather, I'm not getting it. If you get the solution for this, please try doing it or ask your math teacher or somebody. Okay, if they can solve it, then I'll be thankful. Okay, we'll go for the next problem. The next problem is 71. 71, if you see over here, is this. So random variable x is uniformly distributed between 0 and 4. The random variable y is obtained from x using y is equal to x minus 2 squared. What are the CDF and PDF for y? So now you need to take the inverse transformation of this. X minus 2 is equal to root of y, x is equal to 2 plus, plus or minus y. X minus 2 is equal to plus or minus root of y, and x is equal to 2 plus or minus root of y. So one value will be 2 minus root of y, another value will be 2 plus root of y, and that is what we have considered over here. So for 71, range is given as 0 to 4. So if it is 0 to 4, then the value of fxx will be x by 4. Okay, this will be just x by 4. Similarly, the fxx will be equal to 1 by 4, 0, x less than or equal to 4, 0 otherwise. Now, really speaking, we should have written here, this cannot be 0 otherwise. It will be 0 for less than 0. For x greater than 4, it will be equal to 1. Okay, there's a mistake here again. 0 for this capital fxx is the probability, or rather the CDF. This CDF will be 0 for x less than 0. For x greater than 4, the CDF value will be equal to 1. That is the mistake which again I have done here. Please correct it. Okay. But however, fxx is equal to 1 by 4, 0, 0 less than x less than 4, and 0 otherwise. This is all right. Because if you differentiate this, you should get this. If you differentiate 1, you will still get 0. So you will get this equation. So differentiation of the above one is going to get us the fxx, the PDF over here. So why we have written x minus 2 squared, this is given to us. So x minus 2 is equal to root of plus or minus root of y, and that will give us x is equal to 2 plus or minus of y. And that will give us the range of values of x there, and range of values of that x is p of 2 minus of root of y less than x less than 2 plus of root of y. And this is fx2 plus root of y minus fx2 minus root of y. And using that, property of the differentiation there, fy is equal to 1 by, I need to if I need to write fxx for this, and then internal derivative of this, quantity 2 plus root of y, that will be 1 by 2 root y. Similarly, fx2 minus root y, small, so this should be small fx. There's a mistake here. This should be small x2 minus root of y. Internal derivative of that will be 1 by minus 2 root of y. So minus minus will cancel, and that will become plus over here. So we will get that value. Fx of 2 plus root y is equal to 2 plus root y by 4. Within this range, 0 less than or equal to 2 plus root y equal to less than or equal to 4, and that will give us the value of y to be between 0 to 4. Similarly, the other one, fx of 2 minus root of y is this, and that will be again 0 to 4. Okay, this can be solved to be corresponding to 0 to 4, taking the same ranges. Okay. Then we have the quantity which is fx of y, which is the combination of both of them, that is sum of both of them, that will just give us the root of y by 2 between 0 less than y less than 4, because ranges are same for both. Okay. Now, if you want fx of root of 2 plus y, then that will be 1 by 4, 0 less than y less than what you call 4, and you'll get for fx2 minus of root of y 1 by 4, 0 less than y less than 4 again, and you can try to find that totally, and then try to solve it. Then that will give us 1 by 4 root y. This is one way of doing it. Otherwise, you can just differentiate this. If you differentiate this, you'll get 1 by 2 into 2 root y. That will be again 4y. Okay. That's another way of doing it. You need not do all that process. You can just get straight away by, differentiating this y by root of y by y with respect to y. You will definitely get this value. Okay, 1 by 4 root of y. Okay. Then let us go to the what you call 72. I think we are running out of time. 4 minutes are there. I think we can solve one more problem. Okay, 72, let us see what it is. 72 is resistor R are uniformly distributed in the interval 50 plus R minus 5 ohms from the circuit theory. The conductance G is equal to 1 by R. What are the CDF and the PDF for G? So if G is equal to 1 by R, then R will be equal to 1 by G. That will be the inverse. Okay. If G is equal to 1 by R, R will be equal to 1 by G. That becomes the inverse. So using that there, and seeing that we have the ranges of values of resistor to be 50 plus R minus 5 ohms, that is 45 to 55 ohms, we can try to solve that example. So the FR of R, that is the PDF for the resistance, will be the range of these values 45 less than R less than 55. Range is 10, and therefore this will become 1 by 10. Because the range is 10 here, because then it will become 1 by 10. Because total area under this should be equal to 1. 1 by 10 into 10 will become 1. Therefore, this quantity is equal to 1 by 10. This point has to be remembered. This 1 by 10 is got directly from the range of values of this, which is 45 to 55, it is 10. So therefore, this should be inverse of that, 1 by 10. So that 1 by 10 multiplied by 10 will give us the value 1. That just is from the property of the PDF, that area under the PDF curve is equal to 1. And we are telling that it is uniform distribution. Okay, uniform distribution. So FRR will be, you need to integrate this R by 10, 45 less than R less than 55. Again here there is a small mistake. For X less than 45, it is 0. For X greater than 55, it is equal to 1. FRR, capital FRR, the CDF will be equal to 1. So that is again, please correct that. since again now g is equal to 1 by r, we can try to write the what you call function which is equal to fr of 1 by g over here, and that will give us the f of g by g of g will be equal to, you know, we need to write it as in terms of the 1 by g. That will become, we had 1 by 10 and now it will become 1 by 10 g for g values 1 by 55 less than g less than 1 by 45. The range of values of this will be this. Now, if you want to find the CD, what you call PDF from the CDF, the only thing is you just need to differentiate this. So fg small fgg, that is the PDF, will be equal to small fr 1 by g, and the internal derivative of 1 by g is minus 1 by g squared. So now we are left with fr of 1 by g, and that will be the one which we need to substitute, and that is 1 by 10. And we cannot write this minus over here because of the reason that this quantity should be positive. So therefore, generally we will have to write this as plus, even if it is minus 1 by g squared. So therefore, it will be 1 by 10 g squared from the earlier what you call value there. Okay. So it was 1 by 10, and now that quantity 1 by 10 will come into picture, and therefore we'll get 1 by 10 g squared. Okay. This quantity will be 1 by 10, and this is 1 by g squared, and hence that will be 1 by 10 g squared within this range and 0 otherwise. Okay. So thus will